Hi everyone, nice to see some old faces again, and thank you for the invitation. I know that time is short, and I was asked to talk about some of the bioengineering contributions to the COVID crisis, and so I'll just go pretty quickly. We'll have some time for questions later. So what you can see here is basically a dashboard. Sometime about March 15th, this is when I shut down my lab and told everybody to start thinking about writing a paper, maybe finally work on some chapters that we were trying to work on, and maybe write some grant proposals so that when everything's up and running again, we'll have some money to support people. But pretty quickly, we decided that there's really a big need, especially when back at that time in mid-March, we were concerned about this surge, the number of cases that could overwhelm our medical system. And we were all looking at videos from Wuhan, China, and in Italy. Remember that at that time, everything was pretty scary, of hospital workers just getting sick and overwhelmed. And so we decided that I would open the lab to my postgraduate, my postdoctoral fellows. So it has to be postdocs, not PhD students, and then start working with collaborator labs and start working on projects. And pretty soon people find out that we're working on projects, and they started making requests for things for us to do. And so we created a little dashboard of basically keeping track of projects. And what you see here is basically in a little bit over a month, projects that we were working on, going from design to 3D printing prototypes, to engineering build, and then validation of the engineering build, meaning near final production. And then of course, someone has to approve everything before we go into mass production. So that would be me. And then we'll either do it in-house, or we will actually send things out for contract manufacturing using machines that we don't have, like injection molding and sewing machines and things that we simply don't have the capacity for. And so for the next few minutes, I'm going to just go over some of these projects. We won't go over all of them, and we wouldn't be able to get into too much details, but feel free to ask questions. We'd love to learn more about what brilliant ideas our students may have for us. So the first project that came to us was face shield. In fact, the project still comes to us. People are still asking about face shields. If you look on the left side, these are face shields that you will find on Amazon. They look really good. I want some, but you can't buy them. They are not available. In fact, they don't even tell you when they can ship it. And then the middle top, you see the orange face shield. That's designed and made by a very popular 3D printing company, Prusa. And that's open source. Anyone can print this, and it's very popular. One of the issues that some of the hospitals have is that there's an open top where aerosol can basically fall through that area and get into the eyes and nose and faces. So then designs like the blue one you see and the ones on the bottom become to pop up on the internet. This is where they cover the face, so there's less chance for aerosol falling from the top. The ones on the bottom are really the lifesavers for a lot of hospitals. These are actually made by Professor Jacob Schmidt in the engineering makerspace, and this is something that UCLA Bioengineer should be very proud of. They were making hundreds of these a day, and making I don't know how many thousands in the time to basically buy time for us to design what you see on the right, which is injection molded, high quality, advanced polymers that we can sterilize, we can disinfect, we can clean and reuse. But it takes time, just to get this design and then injection molded. So all that time, Professor Schmidt and his team just worked tirelessly to create these stopgap masks, stopgap shields that people can be using. And so they were fantastic. And Jacob's been just amazing. He works 7 days a week in the lab. Whatever we needed, he responds and just get us what we need. So we couldn't have done any of our projects without Makerspace. I just want to make sure that we give them a nice shout out. So the second project that got to us was the idea of making face masks, because as you know, there's a shortage of N95s. And so we went back to the drawing board. There are tons of designs on the internet. You can get them off Thingiverse and NIH sharing sites. What we decided to do was design our own to have injection molded housings on the top left. So that design you can easily injection mold and then custom make our compression mold silicone seal so that we could have a few sizes and would give the best seal to fit around the face. Because it's one thing to have an N95 filter, but if the gap has leakage, then it's basically useless. And then on the right, you see some filter cartridges where we can create different sizes and shapes depending on the material, and then hair savers for the back so that we can apply a lot of compressive stresses to keep these things nice and tightly sealed around the face. And so finally, we then have a completely 3D designed respirator, silicone seal in the yellow, and then the plastic molding in blue, and then a cap in the front. And of course, the biggest supply chain limitation is not the plastic, is not the silicone, but it is this filter. So both from sourcing materials from all over the world to locally to even making our own, these are actually nanofibers that are made in our own lab that are designed to trap particles, and we'll talk a little bit about trapping shortly. But we learned a lot about how filters are made. So it turns out that there are many layers and they serve different functions, and depending on the property, the composition, the diameter of your fibers, and the electrical charge, you could have a completely different behaving material. And this is very interesting to us because it turns out that when we look at what's an N95 mask, if you look at the right side, the definition for the standard N95 is that it removes 95% of all particles that are greater than 0.3 microns. Okay, so if you look at that chart, the pink box on the right is basically 95% of everything above 0.3 microns. If you stare to the left, you see where coronavirus is. It's basically averaging about 0.1 microns, averaging ranges 0.06 to 0.12, depending on the protein folding. And so if you put that back on the plot on the right, you see the corona size range is actually smaller than what the N95 is rated at. And also what you see in this roller coaster blue, yellow region is depending on the size and the mass, different filtering mechanisms, whether it's diffusion, interception, or inertial, or electrostatics, those actually play a role in the fractional collection efficiency, meaning blocking efficiency. And so actually the coronavirus is not in the high collection efficiency range. That size range is actually very difficult for some filters to make. So as we make our own filter materials, we actually have to make sure that we are capturing that size discrepancy. This pretty interesting problem that we didn't realize and make us think twice about how N95s actually work. So we went up and invested heavily in the right materials and the right testing machine. So you see on the top a particle generator that we can essentially control to make particle size in the ranges that we want. And then in the middle, you see a particle counter that is used for standard testing to see if something fits well or not fit well. And you see an example of something that passed. Pass level in the green box is 100 score. And then for the really good N95 mask, the score could be 200 plus, which is very good. And you can see that this is tested while the person's bending, talking, the head is tipping side to side, up and down. And so this is a very useful test that we have, quantitatively measuring. But that's not enough for us, because for us engineers, we have to be a little bit more careful about just total averages. So on the right, you see this nano size analyzer that actually allow us to quantify what size particles are existing and what concentrations. And you can see that it basically covers the coronavirus size range from 0.6 to 0.12. So this is very, very good equipment that we have now to essentially make our own filters or test existing commercial filters and see how well they work. And then if we sterilize it, if we want to put it under UV exposure to kill our viruses, how is that changing the filtering capacity, and at what size range are these particles being changed? So these are very interesting. And of course, we also built our own test unit to look for breathing resistance. So we built a little differential pressure sensor. The NIOSH standard for N95 is less than 343 Pascal pressure drop at 85 liters per minute. So we built the box, and we actually force a mannequin to breathe at 85 liters per minute and see how much pressure drop there is through the mask. It's a very fun project for the team. Lots of cool little engineering. This is a project that is for what's called a powered air purifier respirator, where we have different formats where the doctors or health personnel will wear these helmets, and you see on the lower left, this helmet basically fits around the head, and then there's a shield that covers around the head and neck. And then the NIOSH testing requires this to at least be able to put out 220 liters per minute constantly. And so this battery is basically waiting for 6 hours, and we'll be ready to essentially deploy this. This is already approved by the IT office to be freely shared on the internet, and especially at NIH. So that's why you see on the top here, NIH 3D Print Exchange. We can share this design. We can actually share all the part numbers and have people basically follow our instructions and build this themselves. On the right, you see these shields, these Pepper Shields lens cuff systems that we developed that not just fit our own helmets, but it also fits the existing manufacturers' helmets. And with a little 3D printing, you can make it fit most helmets out there. And of course, the materials are designed by engineers, so you can compare that the elongation to failure is much, much higher than the original manufacturer's materials. And this was also approved for NIH free sharing. So this is very exciting for us. This means that any hospital can use this material and use our designs. This is a project with one of our UCLA Bioengineering alumni, Mark Roden. I think he's actually one of the audience today. Hi, Mark. And he's been working hard with a team of engineers, local engineers, to develop smart vent splitters where one ventilator can be split, but more importantly, they created the sensors and controllers so that if the lung compliance in one patient suddenly goes up, that the air isn't diverted fully into the other lung and potentially damage the very, very tender lung tissue. And they made some fantastic progress in that, and very, very proud of what they're doing. And so that's the search, right? So if you take a look at the time frame, sometime about mid-March to about end of April is when we were working. And meanwhile, this is California COVID death per day. You can see that we got lucky and we really didn't get the surge that we were afraid of, which is a really good thing. The other problem though is that this slope is sort of flattening, but it really isn't going down, right? And so the California numbers are pretty good. If you superimpose, this is the University of Washington projection, you can see that the projection shows that it's beginning to maybe slowly dip down. You can take a look at the bigger picture. The total projection is that it may go down by August, all right? We're hoping that that may be the case. But as you know, the LA County stay at home, safe at home provision is now reordered to have no ending date. It's gonna just keep going until this thing really dies down. Now, the problem for us at UCLA is we live in UCLA County, and LA County has only 26% of the California population, but we have 50% of the cases and the COVID deaths, which means that as this thing evolves, the PPE needs are also evolving. And so what our lab has done initially for the first month for the frontline health workers are going to have to change to also be different to protect more people. One thing that you can already see is that we have to think more about scalability versus customization. So on the right, you can see that 3D printing approach were very popular during the first month to prevent the surge, but that's not really going to be solving the problem when we need a lot more of these. So injection molding approach and other high throughput manufacturing is something that we really got to design for. So, and most of you are engineers that that have done CAD before, you know that with 3D printing, you can pretty much print whatever you design. But with injection molding, that's not the case, right? There are very strict requirements for efficient, high-quality injection molding. And then, of course, there are other choices in between. The MacGyver approach is very popular, where we take stuff off the shelf and we repurpose them to build a new unit. So our Pepper helmet is a good example of that. And then, of course, there's the hybrid approach, where we may combine various degrees of injection molding with 3D printing approach to get the best of all worlds, where we can have high volume, but also some customization. So in fact, our new respirator mask is going to be doing just that. And then the other issue is convenience versus sustainability. We have a lot of things now that are disposable face shields, disposable gowns. These are okay when you're talking about just the frontline people, but when we scale up, you cannot really expect the supply chain or the environment to tolerate this type of abuse. So we have to look at other solutions as disinfectable shields and washable gowns, and this applies to many, many things that we're redesigning. So another problem that we see moving forward is the idea of truth versus friction. A lot of companies are changing their business model. They're making and selling masks and selling face shields. This is from CDC website. This tells you that a lot of things that are supposed to be NIOSH approved, FDA approved, or whatever, these are basically picked out by CDC to tell you that these are all not working. They're not NIOSH approved. And so we're gonna see a lot of that, a lot of false advertisement, a lot of fraud out there, and we just gotta be careful. So this just points to the need for testing. So a lot of the equipment that we invested in for testing, I think could be used for a good public service to really just help people figure out what is real and what is not. And it's going to be done by an independent lab like UCLA. So I think it'll be very helpful. Obviously, we have a lot of work to do in terms of getting our products going to the FDA and also NIOSH approval, but these are not that difficult. It just costs some money, and hopefully we are able to move forward on those as soon as our technologies are ready for those approvals. And just want to spend a minute on the important people that made this happen. A lot of faculty from medicine, engineering, dentistry collaborated across departments. The people in red boxes are all the postdoctoral fellows and PhD students from other labs that have been working on this. The people in blue are the UCLA Bioengineering alumni, and again, Mark Roden on the bottom there. He's definitely a key player in the ventilator project. And special thanks to the Samueli School having the makerspace. Again, without the makerspace, we really couldn't do most of the things that we've done. The staff in the media team, the staff in the development office, purchasing, shipping. We purchase a lot of supplies, and we need them next day, we need them tomorrow, and we've never had a problem with the staff have been so great. And of course, we were able to generate some support from a lot of foundations, Audrey Amos Foundation, Shapiro Family Foundation, Johnny Carson Foundation, and many, many individual donors that I cannot list them all. And of course, industry support from a lot of the local companies. And so you see on the bottom right, this little Uncle Sam, we want you. There's a lot more projects to do. If you're interested in getting involved, contact BMES, contact me. If you know supply chain solutions, if you know manufacturers that want to help, let me know. We have lots of projects. I'm only showing you a little bit of it.